Let's take a look at the second example here. It says analyze and sketch the graph of f of x equals x to the fourth minus 4x cubed plus 5. So what do we usually do? We analyze the original function first. We always want to find the domain. We want to find those x-intercepts, and we want to find those y-intercepts. To find the domain, just consider the type of function in this case. This function's a polynomial function, and because it's a polynomial function, we know that its domain would be negative infinity to infinity. Remember, to find x-intercepts, you need to set the function equal to 0. Here we'd have x to the fourth minus 4x cubed plus 5. Set the function equal to 0 and try to solve. Well, unfortunately, unlike the previous problem where we could factor by grouping, this problem does not have any simple methods of solving this equation. You did learn some techniques in college algebra that might help. For instance, you could use the rational zeros theorem and determine what possible zeros there could be. You could test the zeros and all of that. But in all honesty, if it's not easy to find the x-intercepts, I don't expect you to without a calculator. So we're actually not going to find the x-intercepts for this. We do not need to be accurate on that. Again, we could verify x-intercepts by using a graphing utility or a program such as Desmos. We can, however, always find the y-intercepts. That's easy enough. A y-intercept occurs when x equals 0. So we plug in 0 for x. That'd be 0 to the fourth minus 4 times 0 cubed plus 5. So I'm getting, when I plug that in, 5, which tells me my y-intercept is the point 0, which is the x value I plugged in, 5, which is the y value that I got out. So it looks like on this one, I have a y-intercept of 0, 5. Again, it's a polynomial function, so I know my domain is negative infinity to infinity. So now that we've analyzed the original function, we want to analyze the derivative of the function. So let's look at the original function. We know was x to the fourth minus 4x cubed plus 5. Finding the derivative of this should be easy for you. It's a nice and easy polynomial function. You would have 4x cubed minus 12x squared. Again, you want to find the critical value, so we set that equal to 0 or undefined. This never could be undefined as it is a polynomial function. So what do? Well, I'm going to look at this and I realize that I could take out a 4x squared from both of these terms, factoring it. If I take a 4x squared, what would be left? It looks like I'd have an x in the first term and a minus 3 in the second term. So it seems to me that my first derivative is really in factored form, which is easier to use for a sign chart, is 4x squared times x minus 3, and I'm setting that equal to 0. I set each factor equal to 0. Divide by 4, I'd have x squared equals 0. Square root of 0 is 0. So that's one of my critical values. X minus 3 equals 0. Add 3 to both sides. I'd end up with x equals 3. That's my other critical value. I take those critical values and I throw them on a number line. I have the critical value of 0 and a critical value of 3. Again, I know my derivative is 0 at both of those points. And I break it up to see the intervals. First interval would be negative infinity to 0. Then I'd have 0 to 3. Then I'd have the interval 3 to infinity. I need a test point for each one of those intervals, and I'm going to plug it into the factored form of the derivative. So I have 4x squared times x minus 3. I'm going to pick a number in each one of those intervals. First interval, I'll pick negative 10. Second interval, from 0 to 3, I'll pick a 1. Third interval, 3 to infinity, I'll pick the number 10. If I plugged in negative 10, my first term would be positive, my second term would be negative, and a positive times a negative is negative. Let's try plugging in a 1. If I plugged in a 1, I'd have positive. My second term, 1 minus 3, would be negative, and a positive times a negative is negative. If I plug in 10, first term would be positive. It's always positive because it's squared. 10 minus 3 is positive, so my third interval would be positive. So putting this information back on my number line, my first interval was negative. My second interval was negative. My third interval was positive. Again, that's my first derivative, so let's consider the function. Anytime my derivative was negative, I was decreasing, and anytime my derivative was positive, I was increasing. At x equals 0, I do not change from increasing to decreasing or decreasing to increasing. My derivative stays the same sign. That means it's neither a max nor a min. However, at x equals 3, I do go from decreasing to increasing, which means that point has to be a minimum. Again, a minimum is a point on a graph, so I actually need to plug in 3 to the original function, which I'll do now. 3 to the 4th minus 4 times 3 cubed plus 5. Plug that into my calculator. I'm getting a value of negative 22. So what I have determined is the point 3, negative 22, is a minimum. So let's take that information together. Again, it says, when is it increasing? Well, it was increasing when the derivative was positive, which was the interval 3 to infinity. When is my function decreasing? My function is decreasing when the derivative is negative. This function is decreasing on the intervals negative infinity to 0 and 0 to 3. It might be tempting to sit there and say, okay, let's just say negative infinity to 3 and include the point 0, but remember the derivative at 0 is 0, so it's neither increasing nor decreasing at the value x equals 0. Maximum, the maximum we determined, well, we never determined there was one, so we'll say none here, but we did determine there was a minimum at the point 3, negative 22. All of this information is going to be summarized at the next page when we put it together to build the graph.